Clustering is the process of finding meaningful groups in data. In clustering, the objective is not to predict a target class variable, but to simply capture the possible natural groupings in the data. For example, customers of a company can be grouped based on their purchase behavior. What is the difference between classification and clustering? Categorizing a given customer as high value or not is a supervised learning task of classification task. Segregating a population of customers into different groups based on similar characteristics is an unsupervised learning task of clustering. The process of identifying whether a data point belongs to a particular known group is classification. The process of dividing data into meaningful groups is clustering. Most of the times, it is not known beforehand which groups to form, and thus the identified groups might be difficult to explain. These identified groups are clusters. The data mining task of clustering has two applications: used to describe a given data set, used as a pre-processing step for other predictive algorithms. Clustering a company's customer records and attributes can yield a few groups in such a way that the customers within a group are more like each other than customers belonging to a different group. Depending on the clustering technique used, the number of groups or clusters is either user-defined or automatically determined by the algorithm. Since clustering is not about predicting the membership of a customer in a well-defined meaningful group, for example, frequent high-volume purchaser, you need to investigate the similarities of customers within a group to make sense of the group as a whole. Regardless of the types of clustering applications, the data mining task of clustering seeks to find the groupings in data in such a way that the data points within a cluster are more similar to each other than to the data points of the other clusters. One of the common ways of measuring similarity is the Euclidean distance measurement in n-dimensional space, which is used in many clustering algorithms. You have already learned about Euclidean distance measurement in k-nearest neighbor classification. Before you learn about the different ways to implement clustering, you should be able to define the different types of clusters. On the basis of membership of a data point to identified groups, clusters can be exclusive or strict partitioning clusters. Each data object belongs to one exclusive cluster. This is the most common type of cluster. Overlapping clusters. The cluster groups are not exclusive, and each data object may belong to more than one cluster. These are also known as multi-view clusters. For example, customers of a company can be grouped in a high-profit customer cluster and high-volume customer cluster at the same time. Hierarchical clusters. Child clusters can be merged to form a parent cluster. For example, a long-term customer cluster and a cluster of new customers with high-value purchases can be merged to form the most profitable customer cluster. Fuzzy or probabilistic clusters. Each data point belongs to all cluster groups with varying degrees of membership from 0 to 1. For example, in a dataset with clusters A, B, C, and D, a data point can be associated with all clusters with degree A is equal to 0.5, B is equal to 0.1, C is equal to 0.4, and D is equal to 0. Instead of a definite association of a data point with one cluster, fuzzy clustering associates a probability of membership to all the clusters. Some of the most common implementations of clustering are k-means clustering, density-based spatial clustering of applications with noise, and self-organizing maps. These algorithms follow different approaches to identify clusters in a dataset. In this topic, you will learn about k-means clustering in detail. K-means clustering is a prototype-based clustering method where the dataset is divided into k clusters. K-means clustering is one of the simplest and most commonly used clustering algorithms. In this technique, the user specifies the number of clusters that need to be grouped in the dataset. The objective of k-means clustering is to find a prototype data point for each cluster. All the data points are then assigned to the nearest prototype, which then forms a cluster. The prototype is called as the centroid, the center of the cluster. The center of the cluster can be the mean of all data objects in the cluster, as in k-means, or the most represented data object, as in k-medoid clustering. The cluster centroid or mean data object does not have to be a real data point in the data set and can be an imaginary data point that represents the characteristics of all the data points within the cluster. In an n-dimensional space, where n is the number of attributes in data sets, k-means clustering creates k-partitions. To partition the data set, you would need to define a proximity measure. The most commonly used measure for a numeric attribute is the Euclidean distance. Figure shown here illustrates the clustering of a data set with only two numerical attributes. This data set is two-dimensional with numeric attributes and k is specified as 3. The outcome of k-means clustering provides a clear partition space for cluster 1 and a narrow space for the other two clusters, cluster 2 and cluster 3. The logic of finding k clusters with a given data set is rather simple and always converges to a solution. However, the final result in most cases will be locally optimal, where the solution will not converge to the global best solution. Take an example of a two-dimensional data set and walk through the step-by-step process of finding two clusters. Step 1. Initiate centroids. The first step in a k-means algorithm is to initiate k-random centroids. The number of clusters k should be specified by the user. In this case, initiate two centroids in a given data space. Each initial centroid is given a color so that data points assigned to a centroid can be indicated by the same color. Here, each centroid is enclosed in a circle to differentiate them from the other data points. Step 2. Assign data points. Once the centroids have been initiated, all the data points are assigned to the nearest centroid to form a cluster. In this context, the nearest is calculated by a proximity measure. Euclidean distance measurement is the most common proximity measure, though other measures like the Manhattan measure and Jaccard coefficient can be used. The Euclidean distance between two data points x and c with n attributes is given by distance d is equal to square root x1 minus c1 whole square plus x2 minus c2 whole square plus so on plus xn minus cn whole square. All the data points associated to a centroid now have the same color as their corresponding centroid. Step 3. Calculate new centroids. For each cluster, you can now calculate a new centroid, which is also the prototype of each cluster group. This new centroid is the most representative data point of all the data points in the cluster. Mathematically, this step can be expressed as minimizing the sum of squared errors SSE of all data points in a cluster to the centroid of the cluster. The overall objective of the step is to minimize the sum of squared errors of individual clusters. The SSE of a cluster can be calculated by the equation shown here, where Ci is the ith cluster, j is the data points in a given cluster, mu I is the centroid for the ith cluster, and xj is a specified data object. The centroid with minimal SSE for the given cluster I is the new mean of the cluster. Step 4. Repeat assignment and calculate new centroids. Once the new centroids have been identified, assigning data points to the nearest centroid is repeated until all the data points are reassigned to the new centroids. You can see the change in assignment of two data points that belong to different cluster in the previous step. Step 5. Termination. Step 3 of calculating new centroids and step 4 of assigning data points to new centroids are iterative until no further change in assignment of data points happens, or in other words, no significant change in centroids are noted. The final centroids are declared the prototype data objects or vectors, and they are used to describe the whole clustering model. Each data point in the dataset is now tied with a new clustering ID attribute that identifies the cluster. Even though k-means clustering is simple and easy to implement, one of the key drawbacks of k-means clustering is that the algorithm seeks to find a local optimum which may not yield globally optimal clustering. In this approach, the algorithm starts with an initial configuration and continuously improves to find the best solution possible for that initial configuration. Since the solution is optimal to the initial configuration, there might be a better optimal solution if the initial configuration changes. The locally optimal solution may not be the most optimal solution for the given clustering problem. Hence, the success of a k-means algorithm very much depends on the initiation of centroids. This limitation can be addressed by having multiple random initiations. In each run, you can measure the cohesiveness of the clusters by a performance criteria. The clustering run with the best performance can be chosen as the final run.